Good evening, everyone. Good evening, friends. So, welcome back to our sessions on RNN, Recurrent Neural Networks. So, in the previous session, we have understood, why traditional neural networks like ANN and CNN cannot be used for sequential data, right? So, we have quickly recapped ANN and CNN, and we have also understood what is sequential data, right? So in this particular session, we are going to get introduced to RNNs, specifically recurrent neural networks. How do they work? The architecture of RNN. Then we'll also understand the types of RNN and uh, time permits. Yes, we'll also discuss the variant of RNN. It's bidirectional RNN. Okay, so before we start the class, before we start our session, I would like to quickly, go through our YouTube channel. So friends, if you are joining this session for the first time, so we have done multiple sessions on the emerging topics like CNN. Okay, a separate playlist is available for CNN. Then we have a playlist on NLP, natural language processing. Then we also have a playlist on ANN. Then we have a playlist on regression, classification, SQL, Power BI, and Python, right? So in this way, we have all the important topics as different playlists. And I would like you guys to subscribe to our YouTube channel because we are going to plan you know wonderful sessions in the upcoming future as well, right? Yep. So what is the main drawback of not using traditional neural networks like ANN? Sorry, just give me a minute. So what might be the reason, friends? Why are we unable to use ANN and CNN as for hmm, okay, let me go back. That's- You see here, so we have discussed the topics of ANN and CNN, right? So the main reason why we are unable to use ANN and CNN for sequential data is, you know, for ANN and CNN, as part of the input layer, the number of neurons has to be fixed. Am I right? Yes. But since it is sequential data, okay, where the sequence matters, okay, the examples we have it as time series data, text data, okay. So if you take especially text data, can you fix the number of words in a sentence? Obviously not, because one sentence may have just only 4 words, but the other sentence may have 40 words, right? So when the number of words get changed, obviously we cannot just fix our input layered neurons, you know, fixed. So that might cause the first reason, the traditional neural networks like ANN and CNN can be used for sequential data. See, handling variable and sequences. Okay, then moreover, ANN and CNN don't have any kind of hidden state which actually acts as a memory. Okay, so what is this hidden state? We'll understand as part of this session, friends. Right? Yes. So RNNs, which stand for recurrent neural networks. Okay, so they are especially designed for handling sequential data. Okay, sequential data is the data in which the order matters. Okay, you take time series data. So time series data is the data which is captured in the sequence of time. Then you take text data. In text data, the next word with respect to any sentence, within a sentence, each and every word will be decided based on the previous words, right? In order to give a meaning at the end of the sentence, we have to focus on the previous words that were being used as part of the sentence. So such kind of data is called sequential data, and moreover, RNNs, they have a memory uh, component. This is actually capturing the information that is part of the previous inputs. So this particular memory component is not present in ANNs and CNNs. No. Okay. So the main idea behind RNNs is, they help us to process the inputs one at a time. What do you mean by one at a time? So if you take a sentence, okay, for example, I'll take introduction to RNNs as a sentence. So if you take this sentence, introduction will be taken at once, then the next word two will be taken, then finally RNNs. So it just takes one input at a time, then it updates the hidden state at each step. So at each and every step, the hidden state gets updated. So this particular hidden states, it acts as a memory for storing the information. What exactly is hidden state? You'll understand as part of the architecture, friends. Right? So just hold on. Yep. So the key features with respect to RNNs are memory. Okay, this is where the hidden state captures the information based on the past inputs. So based on the previous inputs that we pass as part of the training, okay, this is going to capture the information, and the parameters that will be used will be shared across the entire neural network. Okay, so the same weights will be used. You take the weights with respect to the hidden state, or the weights with respect to the inputs, or the weights with respect to the output. The same weights will be used across all the steps. Okay, this is going to actually reduce the number of parameters. If you take any other, neural network, the number of parameters, they keep on increasing. As the training journey happens, the number of parameters increases. But in traditional RNNs, what happens is, since the weights are being used same across each and every, layer, so the number of parameters will not be increasing. Okay, it keeps constant. And the main advantage of RNNs is they can handle, varying lengths of input data. So the data might not be fixed in size. Even though if the data has varying length, yes, they are flexible to handle such kind of sequence data, right? So RNN architecture, if you observe, RNN architecture have especially three layers. It has three layers. Okay. So the first layer is input layer. As part of the input layer, the input will be passed at a time step t. Okay. So everything is captured with respect to the time. Okay. So if you take a word in a sentence, okay, or a value in a time series, assume a data. Either it might be a word or it might be a value within a time series data. Okay. So each and every word will be taken one at a time. Then it will be passed to the hidden state. Okay, so within the hidden state, what exactly happens is it also uses the memory of the previous inputs. So together it works and learns the pattern. So probably I have to show you the diagram. Just give me a minute. Yes, you see here. Yep. So this is the architecture of RNN. Okay, in which we have um, an input layer and a hidden layer and output layer. Only three layers. That's it. Input layer, followed by hidden layer, and finally output layer. Okay, so how RNN work is what we are going to understand initially. Okay, so if you take RNN, a input will be passed one at a time at a given timestamp. Okay, so let me take this particular, you know, this particular case. So if you see here, at time t, I'm passing an input x. So I'm representing it as xt. So once the input get passed to the hidden layer, what exactly happens in the hidden layer is it uses an activation function. This activation function might be tanh, relu, whatever it might be, friends. ALU, leaky relu, it depends. Okay, so it uses an activation function, and moreover, it uses the hidden state, the output of the previous inputs, and gets trained. So at each step of RNN, the process units with a fixed activation function. And these units have an internal hidden state that acts as a memory. So within, these hidden state, there are some units which acts as some memory. Okay, and they are capable of retaining the information from the previous steps. So they are helping us to, retain the information from the previous steps as well. So this particular memory allows the network to store the past knowledge and adapt based on the new inputs, right? So here is the mathematical representation. You take a hidden state. So within hidden state, what happens is an activation function will be used in which, so for each and every input, there will be one weight assigned. Yes. So if I'm taking the input as xt, okay. So at time t, the input that I'm passing is xt. See. So to this, the weight gets multiplied. Yes. So the weight that I'm considering is wt. Okay, wt. Sorry, wx, because the weight that is relevant to the input. So wx will be multiplied by xt. Then what about this b? B is nothing but the bias. The bias term that gets added to the function. Then what is this wh multiplied by h at t minus 1? That is nothing but the output that you get from the previous stage. Okay, so at t minus 1, this is at the t time, right? Okay, at t minus 1, you'll be passing one input. Yes. So when you pass an input, you'll obviously get an output over here from the hidden state. So that hidden state from the previous step, I'm representing as h at t minus 1. Okay, so this h at t minus 1 will be multiplied with wh, which is nothing but the weight matrix for the hidden state. So the weights are fixed, friends. These weights doesn't change. Okay, if you take weight matrix for hidden state or weight matrix for the input or the weight matrix for the output, they will be constant, wh, wx, and wy. Right? So I take these three terms. Additionally, you know, Since I'm going to work on the hidden state, so WH multiplied with H at t minus 1, okay, plus the input that you get at t is equal to time t. Okay, it's nothing but xt multiplied by its weight. Corresponding weight is Wx plus the bias term. So all these terminologies will be added, will get summed up, and that will be passed to the activation function. It might be any activation function. In this way, it gets calculated and the output will be captured as part of ht, which represents the hidden state at time t. And this will be used for calculating the output for hidden state at time t plus 1. So in this way, the previous layered uh, hidden state outputs will also be included as part of the calculations. Okay, so that is the reason hidden state helps us to be, it acts as a memory component for storing the information. I hope it's making sense. So this is the main, working principle of, you know, RNN. And once after calculating the hidden state, the output calculation is also present. Okay, where we use one more activation function depending on the type of use case that we do. Okay, if we are working on a multi-class classification, obviously we are supposed to go and use softmax activation function, right? So the function is given as like this. Initially the weighted sum has to be calculated. So what is the weight associated with ht? It's wh, right? So the weight component that is associated with hidden state is wh multiplied by ht, the hidden state, plus the bias term. Okay, so we have bias for the hidden state as well as the bias term for the output, right? So when you pass all the weighted sum to the activation function, you'll get the output. So this output will be stored as part of yt. Nothing but the y represents the output at time period t. So this is the architecture of, RNN, Recurrent Neural Network. It's very simple. Okay, so recurrent means repeating the same. Okay, occurring repeatedly is nothing but recurrent. So that's what you're doing time again. You're taking an input, okay, multiplying with its corresponding weight. Then you're also using the previous layered hidden state, okay, and multiplying with its weight, okay, adding the bias term to calculate the hidden state of your current step. And once after calculating the hidden state output, you'll be using it to calculate your output for that layer. Okay, for that input at that timestamp, you'll be calculating your output. So in this way, you'll be keeping on repeating the same process. So this is called forward propagation. As part of ANN, the neural networks, we understood forward propagation as well as backward propagation, right? So in this way, we forward propagate throughout the network, right? So now let us talk about the backward propagation. Is backward propagation mandatory? Yes. Friends, you see, or you take any neural networks, ANN, CNN, RNN, it might be anything. We are using the parameters called weights bias. So all of these values, weights and bias are randomly assigned initially. They get initialized randomly, and in order to reduce the loss function, what is loss function? I want you guys to respond. What is loss function? Actual minus predicted will give you the loss. So once after calculating the loss, you'll also calculate the cost. So in order to minimize the loss, we have to back propagate. We have to back propagate. So this back propagation is done to update the weights and bias term. It is done to update the weights and the bias. So that is the purpose of back propagation in neural networks. Very, very important question. What is the purpose of back propagation in neural networks? I hope it's making sense. So now let us understand what is this back propagation through time. Because if you take back propagation concept either in ANN or CNN, there is no time involved. Am I right? Yes. But here the time is involved. The reason is, you'll be back propagating one, no, from this is forward propagation and this is backward propagation. In order to backward propagate, you are supposed to update the weights of each and every, component. All the parameters has to be adjusted, and moreover, the bias will also get updated, right? So this is a chain rule which happens as part of back propagation through time. Okay, so initially the gradient will be calculated. Okay, so once after calculating the gradient, it will be divided with respect to the dependencies. Wherever we have the weights that has to be adjusted, it might be the weights that we have for the hidden state, the weights we have for input layer, the weights we have for corresponding outputs. So for each and every layer, we have corresponding weights. So we are going to calculate the gradient for the loss divided by the weights. Here we have the terminology, friends. Okay. Then we also handle the dependencies in layers. Okay. In each hidden state is updated based on its dependencies. So if you take H3, okay, so the weight with respect to the H2 will be multiplied plus the bias, and sigma is representing an activation function, right? So the dependencies has to be adjusted. Only then the weights that we have in this layer gets updated. Then the same with respect to gradient calculation with including explicit and implicit parts. Okay, and the final gradient expression will be calculated. This is more of calculations. Okay, where we update the weight matrices for the inputs, output, and the hidden states. If you see here, H3 is depending on H2. Am I right? Yes. Then H2 is depending on H1. H1 is depending on H0. So in this way, in order to update the weights, I have to update all the components one by one. So this is nothing but back propagation through time. Now let me talk about some types of RNN that we have. Okay, so recurrent neural networks has some types and they are broadly classified into 4 types. One-to-one RNN, one-to-many RNN, many-to-one RNN, many-to-many RNN. Okay, so these are the types that we have. Let me talk about one-to-one RNN first. So in one-to-one RNN, the architecture is very simple. You just have only one input and one output. You see here in the image, it's very, the architecture is very simple. It's not complicated. You have input, you'll get an output. In the middle, you have hidden state. That's it. So this is the simplest type of RNN, okay, where there is only a single input and you'll also get a single output. Okay, and where is this actually used? Whenever you want to perform classification task, okay, such as binary classification based on some only one feature. Okay, so there we use one-to-one RNN. And in this kind of scenarios, we don't use any kind of sequential data. Sequential data is not preferred. The main reason is if you have sequential data, obviously there are multiple inputs, right? So one-to-one RNN is generally preferred for straightforward classification tasks. Now let us understand what is one-to-many RNN. Okay, so one-to-many RNN is used where we have a single input which is producing multiple outputs. Just think of using one single output, can we get multiple outputs? So this is the architecture of one-to-many RNN, where there is only one input but multiple outputs. Okay, so this is generally used in tasks where one input triggers, a sequence of outputs, predictions. I'll just give you a best example. You take an image, a single image, and pass it to the input layer. So, as we are aware that in input layer, it takes only one input at a time, right? So when you take a single image and we use it as an input to generate a sequence of words as a caption. So how many outputs you can get? Multiple? Yes, I can get multiple outputs. See, I'll take an image, probably, as okay, probably an image that was generated by AI itself. I'll pass it through the input layer. It understands the patterns in as part of the hidden layer and it starts giving the outputs. It gives the predictions. And probably these predictions one by one, I'll get the captions, what exactly we have it in the image. I'll get the caption. So obviously I'll get multiple outputs. So this is one to many. One input giving multiple outputs is one to many. Making sense? Then we also have many to one. So that means many inputs will be used to generate only a single output. Any example, Akhil? Yes, there are multiple examples, friends. If you do sentiment analysis, that is the best example. So even now we have done a use case on sentiment analysis under NLP sessions. So if you haven't watched our sessions on NLP, natural language processing, do watch our sessions on NLP as well. Okay, I'll take multiple inputs, obviously a text. Okay, I'll take a sentence and I'll pass each and every word as an input. So probably it's nothing but you are passing multiple inputs and they get trained as part of the hidden state, hidden layer, and it is going to generate only a single input. So talking about the sentence, either it is a positive sentence or a negative sentence or a neutral sentence. Yes. So task like sentiment analysis is the best example for one many to one RNN. Okay, then we also have many to many RNN. Okay, in many to many RNN, we pass multiple inputs and the output will also be multiple. Okay, so you pass multiple inputs and you get multiple outputs. Examples, language translation. Okay, if you want to, do language translation from, English to Hindi, or if you have language, probably your text is in one language and if you want to translate to the other language, that is the best example for many to many RNN. Okay, you take a sentence in English language and translate it to French. Yes, obviously you get many outputs when you pass many inputs. So this is a many to many RNN. So I hope it's clear. These are the types of RNN. Okay. But the challenge that we have observed as part of RNN is RNN, undergoes the problem of vanishing gradient. So friends, what is this vanishing gradient? What do you mean by vanishing gradient? This was already discussed as part of ANN, right? What do you mean by vanishing gradient? No idea? Right, anyways. See, you take the vanilla RNN model in which it has a single hidden layer and the weights are shared across the time steps. The weights does not change in the forward pass, right? Obviously, the weights get updated as part of backward propagation, but the weight matrices that you'll initially generate will be constant. Okay, and they'll be shared across the time steps. You take different time steps at t is equals to t minus 1, t is equals to t is equals to t plus 1. At different time steps, the weights get shared. So these vanilla RNNs are generally, suitable for learning short-term dependencies, but they are limited by the vanishing gradient problem. So which is discussed as part of, ANN sessions. Vanishing gradient is nothing but the gradient that you calculate. See, once after the forward propagation is done, you'll get the prediction. And once if you get the prediction, you'll calculate the loss. So this loss has to be minimized. That is the objective, right? In order to reduce the loss, in order to minimize the loss, we perform backward propagation. When you propagate in the backward direction, obviously you calculate the gradient dou L by dou W, derivative of loss divided by derivative of weights. And if the gradient gets vanished, okay, if there is no learning, okay, so obviously no, the loss will not be minimized. It will be same even though if the number of epochs keep on increased, there is no change with respect to the output. So the gradients become very small as they propagate backward through time. Okay, when they propagate backward through the time, the gradients they become very small and sometimes they become zero also. So this make a difficult challenge for RNN to learn long-term dependencies. Okay, so that vanilla RNN can just be used for short-term dependencies, but if you have data for long-term, that cannot be suitable. Vanilla RNN cannot be suitable for such kind of data. If not, exploding gradient problem is also observed. Gradient sometimes becomes very large, okay, and this causes instability during training. So the gradient can explode as well. For this, we have a variant of RNN called bidirectional RNN. This is very, very important. Bidirectional RNN. What is this bidirectional RNN? What do you mean by bidirection? General English. What is the meaning of bidirection? Bidirection is nothing but two directions. Am I right? Yes. So this bidirectional RNN helps us to overcome the problem of RNN, where it processes the input in sequences in both forward and backward directions. So if you take RNN, the input sequences are just processed only in the forward direction. But bidirectional RNN helps us to process the input sequences, the data in both forward as well as backward directions. Okay, so why? Because to overcome the problem of vanishing gradient, they have come up with, our statisticians have come up with bidirectional RNNs. And this bidirectional RNN helps us to capture the information both from the past and future context at each step. So different steps, it is going to capture the information from the past data as well as the future data. Yes. So future data, you mean, I mean the text. For example, if you take a text, okay, so especially, um, you know, different words might be same, but if the same word was used in different sentences, okay, the meaning for the word gets changed. The best example, if there are two sentences like this, I love apples is one sentence, okay, followed by Apple launches a new mobile in the upcoming year. So if you take Apple in both the sentences, do they have the same meaning? No, obviously no, because the first in the first sentence, apples represent a food. It is representing a fruit, but the apple that we have in the second sentence is representing an organization. So this bidirectional RNNs helps us to capture the information from the past, that is nothing but the first sentence, and the future context at the same at each time step. Okay, at the same time step, it helps us to understand the information from both the context. Why? Because it processes the data in both directions. So if you understand the components of a bidirectional RNN, probably you'll get the you know uh, clear picture. So the forward RNN, we are aware that process the sequence, the data will be processed from left to right. So this is how it processes. But backward RNN is where it processes the sequence of data from right to left. So you combine both of these. That will be the output for bidirectional RNN. The output of the forward and the backward RNNs are combined. You know, in short, they are concatenated to produce the final output. So probably I have to show you the architecture. You see here, we have inputs at different time steps. So this is the input at t is equals to t minus 1. This is the input that we have at t. Then we have an input x at t is equals to t plus 1. So different inputs. Now, as part of the forward layer, the data, the inputs, the data gets processed from left to right. Then as part of backward layer, the data, inputs get, processed from right to left. Okay, so you can clearly see here the hidden state, how the hidden state is given, the mathematical representation for the hidden state. The equations, everything is same, friends, but here, as the name suggests, bidirectional RNN, we'll have, two RNNs working similarly, and the output is concatenated. You see here, so for the forward RNN, you'll get an hidden state. For the backward RNN, again, you'll get a hidden state. So combined output is nothing but, concatenate both of them. Add up. So when you add both of them, you'll get an output. So that will be your overall output for your bidirectional RNN. Okay. So the limitations that we have are bidirectional RNN is generally, it is computationally complex. Okay. Because, it requires the processing time to sequence, not to, process the data in both the directions. So computationally, it is burden. Okay. In the same way, moreover, it's not suitable for real-time applications. So that is the reason they have come up with LSTM, long short-term memory. Okay. So that part, we'll be seeing it in an use case. Okay. So in the next session, probably we'll come up with a use case for RNN, friends. Okay. So where we'll be predicting stocks. Okay. So taking data on stocks, we'll be predicting how stocks can be predicted. So it's a time series data. Obviously, we can predict it using RNN, sequential data, right? So we can, predict using RNN as well as LSTM also. Okay, this bidirectional RNN will be used as part of LSTM, and that will be explained as part of the next session. Right. So I'll stop it here. If you have any questions, feel free to ask. If not, you know, my sincere request is just go through the previous sessions that we have completed on ANN, CNN, then even NLP, Power BI, SQL and all. Okay, also ask your connections to join the sessions and ask them to learn these important topics as part of AI, artificial intelligence. And moreover, soon we are going to launch a program on Python from 16th of this month, April. Okay, so do share across your connections. This will be a complete course on Python, which will be for 30 to 45 days. Okay, starting from scratch, means from basics till, oops, core and advanced Python along with NumPy and Pandas modules we are going to cover. Right? So friends, before you leave, hit on the like button, and also if you have any kind of questions, post them in the chat window. Okay. If not, whenever you're going through the session, if you find any issue, a query, if it is raised, do post it in the comment section. We'll reply it as soon as possible. And the feedback link has been provided. Share your valuable feedback before you leave. Thank you so much, friends. We'll meet in the next session. Until then, take care. Have a great day. Signing off.